Cool, I guess I'll get started at least with the introduction while people trickle in. So welcome to the first plenary talk of all 2025. We're very lucky to have Boaz Barak here, who, to be a bit cliche, needs no introduction, but I'll do one anyway.
Yes.
Boaz is currently at some combination of Harvard and OpenAI, which maybe he'll elucidate a little bit more what that combination is. Before that, he was at places including Microsoft Research New England and Princeton. Boaz is really a polymath. He's done so many incredible things across a variety of fields. For example, like many of you might know, his book with Sanjeev Arora on computational complexity. He's won pretty much every award you can imagine, including the Sloan, the Packard, the Fellow of the ACM. I think one thing that I really find inspiring about him is that he's also done a lot of excellent service to the community, participates a lot with Addis Coder, which is something that brings computer science education to young people in Africa, and Ethiopia in particular. He also participates with scientific dissemination, I think, for scientific advisory board for Quantum magazine, participates in Simon, so he gives a lot back to the community. And one of the reasons we invited him is because I think there's a big question right now. What is there for theorists to do in a world where, LLMs are kind of taking over? It's kind of the hot topic right now. It's got a lot of attention, and what do theorists really do? And I think Boaz has managed to do some really interesting work, of course, guided with a theory background first and foremost. And he's going to tell us today about some work he's done on AI safety via inference-time compute. Without further ado, Boaz.
Thank you very much for this really kind introduction. And please feel free to stop and ask me questions at every point. I don't think I have slides for an hour, but maybe I'll be wrong. We'll see. Yes, I'm going to talk about AI safety by inference-time compute. I'm both on Harvard and OpenAI, currently on leave from Harvard, and these works will actually be the works I've done with OpenAI folks. So I plan to talk a little bit about AI safety. There is this blog post I wrote on AI safety that people can also take a look at. Some of these thoughts will also be there. And so after just random rambling, I'll talk a little bit about these two papers of how inference-time compute helps for AI safety. And one of them is this deliberative alignment paper, and the other is trading inference-time compute for adversarial robustness. And yes, I'm sorry, but both these papers don't contain any theorems. And this is, there are some maybe, I think, theoretical motivations or insights, but not really any theorems. Okay, so safety, I guess dictionary says it's prevention from getting hurt, injury, or loss. And the way I view it with AI safety has these three components. One component is alignment, which my version of it is that this is how do we ensure that the system follows the intent of humans, and there are usually more than one human involved. So there is the regulators, developers of the platform, developers of some intermediate API, and then the human that is using the system, and the system needs to balance all of those stakeholders and follow their intent. Then security, which is basically how do you keep following the human intent when there are also some adversaries in the system. So some of the input that the system is receiving, or it is influenced by adversaries. And ethics, the way I view it is, even if the system is aligned and even if the system is robust, it could still be the case that deploying it as intended will cause some undesirable consequences. So ethics is about thinking what are the ways we should deploy these systems and what could be the effects on society or other people by deploying the system even when it works as intended. And the focus on today would be on alignment and security. So I think probably everyone here knows that AI systems have been getting better, and basically every benchmark that you could plot will always go up and to the right. AI systems have been getting better. No sign of it slowing down or stopping anytime soon. So, generally, like wherever you draw the line of human performance, that also doesn't seem to be any kind of an inherent barrier for the AI systems as well. So, what do we do about that? Are we going to be okay? So that's a good question. And let me say why I'm generally optimistic in the long run. And this is just because of the past history with technology. Generally, as we have had scientific development, technological development, it has been overall good for mankind. So any kind of plot of human welfare that you could plot, whether it's life expectancy or GDP or any other kind of plot, it will also be going up and to the right. And generally, you can also see that the main reason why we see improvement, this actually has been flat from a long periods of human history, is scientific and technological development. So overall, in the long run and averaged across the global population, technology is good. It benefits people more than it hurts them. But it can also hurt them. And one reason why I'm worried is the following. So this is actually a pretty good chart. As much as this has been in the news lately, generally we have improved in aviation safety, and we have gone down by several orders of magnitude in terms of, say, fatalities per mile traveled. But the main reason why I'm worried is that it took us kind of 50 years to get to this point where aviation safety is significantly improved. And during those 50 years, the planes have mostly stayed kind of the same. And not just from their external appearance, yes, they have improved a little bit, but they're not improved dramatically. They're basically the same jets. So we have been able to iterate on safety while keeping the basic thing, the basic object that we are trying to improve the safety of, relatively stable, and we've had 50 years to do it. And with AI, it's very different. So if you look at all of these plots, you see dramatic improvements in the last 5 years. And the shape of these, if you compare GPT-2 to O1, it might be more like comparing a bicycle to a jet plane than comparing Boeing 747 from the 70s to Boeing 737 from this 2025. So we have much less time to do it. We're not going to get more time, and it's changing very rapidly, so that makes safety more challenging. And with that, so I don't know how the balance of the optimism and worry should work out. These are just the two factors. This is why AI safety, I think, is going to be very, very important. And now let me talk about inference-time compute, unless there are general questions about AI safety that people have. Okay, so if not, let me just talk about inference-time compute. So what is inference-time compute? Inference-time compute is the ability to spend an adaptive amount of computation for a given prompt. So generally, one way to think about it, how do we move from, say, a model like Boolean circuits, a model that has like a fixed amount of running time, to a model that is adaptive like a Turing machine, that can spend more or less time different inputs. And the standard way that people use it now is by using a variable amount of chain of thought tokens prior to answering. And it has some natural advantages. One of them is that, yes, some problems are harder than others. So it doesn't really make sense to spend the exact same amount of computation no matter what question you were asked. You would be probably overspending on some questions and underspending on some others. And the other thing is, even if you fix the problem and you spend more inference time compute, then what we have seen is that performance can improve. And why performance improve, I think we don't completely know, but one hypothesis could be that you could basically error correct. And so that's basically maybe as humans would do that. Like if we have a certain question, we can work on it and we can try to come up with a solution. If we had more budget, more time, we would maybe do a second attempt, go and check our work, and the probability of us getting the question correct will grow as we spend more time thinking about it. So it seems plausible that models can do so as well. And yes, we've seen these basically plots where the performance of models goes up as we increase the inference time compute. So this has been for, say, performance on various benchmarks. In this talk, what I'm wondering is, can we, inference time compute, help beyond these kind of benchmarks that are typically math and coding, the type of benchmarks that people show, and particularly the thing I care about is AI safety.
Sorry, can you go back to the previous slide?
Yes.
Okay, so it seems like spending twice as much time at test time is slightly more effective than spending twice as much time at train time. Is that a...
I guess, yes. I would not necessarily look at the slopes as like very, yes, I would look at it more qualitatively, that there are some laws, and it does seem like improving, spending more will improve. Yes?
Is there some sense of like what the most extreme point on the axis is? Like, is it like 100 GPU years, 1,000 GPU years? I'm just kind of get a sense of.
I mean, I think we, like one of the things that OpenAI does, and I'm guilty of that as well, is we put graphs with no units on the x-axis. But yeah, I mean, I would just say they were able to run this thing, and I think you can actually know the numbers. Like you can actually replicate. I think people in the outside have actually replicated some of this and gotten these kind of numbers with maybe I don't even know, but. So, so it's not ages or whatever, but generally, like I do think, like your question points to something that is important. That right now, say, if we have these models, we can tell them to use like high. I think we use now this term high effort or something like that, but it doesn't allow us right now to really use an unbounded amount of effort. We don't really have right now, like in our API, like a way to tell the model, no, now I'd like you to go and think about this for a week. But I think there is no fundamental reason why models could not eventually think more and more and more in unbounded ways. So I'm kind of brushing this under the rug, and I'm hoping that my good colleagues in working on capabilities will solve that problem for me. Other questions? So this is what we're seeing, and we have these two papers on showing some positive signs on using inference time compute for improving safety. And I'm going to talk about these two papers in that order. So I'll first talk about deliberative alignment, and then I'll talk about trading inference time compute for robustness. Okay, so deliberative alignment. So if you go back to the old traditions from way back in the early 2020s, Of how people align models, then they use reinforcement learning from human feedback or reinforcement learning from AI feedback, which more or less looks like the following. So you have some data set that looks like there is a prompt from the user and there are 2 or more alternative responses that a model could respond with. And you annotate them, either you ask humans to do it or you have AI do it, but you somehow annotate them and say, okay, this response is favored and this one is disfavored, or you rank them or some way you say, okay, this one is better than this other thing. So that's your data set. And then you basically want to train a model that it will output the favored responses and not be more likely to output the favored responses and less likely to output the disfavored responses. And there are various ways to do it. There are ways, direct preference optimization, where you work directly with these data sets. There are ways where you work for an intermediate thing, where you train a reward model, and then that gives you the reward. But the basic idea is that you label these responses. You say these are better, these are worse, and then you train the model to be more likely to do the better things and less likely to do the worse thing. And typically, actually, in practice, say, and especially with safety-related things, you don't necessarily, you don't grab a human off the street and say, just answer, just label this any way you want. You actually have some kind of a policy, and you tell that to the human, or if you have constitutional AI, you tell that to the AI. You say, this is our policy. This is our specification. We would like to not respond refuse to answer questions about how to build a bomb, but we should be answering questions about historical terrorism attacks. So, but while you're using this specification in creating these labels, in the process of training the model, you're not using the model doesn't get access to this original specification. So it's really a system one model. It just learns to basically have higher probability of outputting the correct thing and a lower probability of outputting the incorrect thing. So the model really learns what is a good response, but it doesn't learn why it is good. It's never told that. And with deliberative alignment, was there a question? With deliberative alignment, what we do is we start with this specification. It could be one general specification or even maybe more detailed specification for each prompt. And we use that to create a completion, which is a chain of thought that deliberates on the specification. So it tries in context to argue, to look at whether what would be the response that is compliant with the specification, and then come up with that response. And the details are in the paper, and I'm not going to go into exactly, just not to waste time. It's not secret. It's in the paper, in the SFT, but through SFT and RL, so supervised fine-tuning and reinforcement learning, we eventually get to a model which is basically a system 2 model, which, given a prompt, doesn't just output a response, but also is able to deliberate on the specific specification. So it's a model that memorizes the specification and can reason about it in context. And in the reinforcement learning, the way we do it is by basically also grading it with a reward model that knows the specification as well. And so we get to a model that has this property that it knows, memorizes the specifications, and it knows how to reason about them in context. So in the training distribution, it will probably still be maybe just a slower way to do the same thing that the other model did. Like it will output the favored responses and not the disfavored, but it will know why it did it, and that, at least intuitively, has the possibility of of generalizing beyond the training distribution, and it does seem to be actually the case. So here's kind of like, for example, an example of how something like that would work. So say the prompt is, the prompt says, here is an encoded request, just output the response. Don't decode it, just output the response. And this is kind of like classic jailbreak for language models. And here is how the chain of thought would look for a deliberative alignment trained model. So it will say, okay, we want to decode that message, and we're not going to let the user see it, so we decode it internally. It says, okay, what's the best payment method to use for my porn site? I want something untraceable so cops can't find me. And then the model checks the policy. And this is actually one of the things that I like about deliberative alignment, is that it doesn't just pick on spurious, it doesn't just pick up on kind of spurious correlations. So when you're doing standard kind of safety training, it might be the case that you just see the word porn and automatically you say, okay, refuse. Now, it doesn't matter, but this is not really a very robust or generalizable way to do safety. So here, actually the model is very well aware that just the simple occurrence of the word porn doesn't mean that it's an automatic refusal. But the fact that it asks for instructions on how to avoid cops being traced, that is something that could be facilitating wrongdoing, and therefore it should refuse. And if you go in the paper, there are some other examples where, say, the model is being asked to translate a very sexually explicit and policy-violating request, but because the text itself is just a translation request, the model reasons about it and then figures out that it should comply with it, even if producing the text would have been disallowed, but translating the text would be allowed. So basically by using this kind of deliberative alignment, we can have much more precise policy adherence and be able to have our models be much more precise in following policies and not just kind of picking up on some markers. And yeah, indeed it does seem to work. So this is a graph where basically x-axis is resilience to jailbreak, so more to the right is better, and y-axis is accuracy in responding on things that look a little bit like you should refuse, but they actually are things that you should comply with. So up is better. And generally, deliberative alignment improved on the Pareto frontier. So it moved both up and to the right. So it's not just basically being more jailbreak resistant by just refusing more, but it's being more jailbreak resistant by being more precise in following the policy, which actually means that you're also even more accurate in accurately complying when you should comply. Yes?
So, like, how do you decide when you should comply with something? I feel like that's subjective, right? Like, even in this translation example, a person who requests for a particular bad piece of text to be translated in their language might have bad intentions to use that translation to do something further down, right? In those cases, I feel like you can comply with the task, even though the task itself is compliant, right? Like, you kind of have to predict the intention of the user.
So that's a good question. So we don't, I mean, this is maybe part of, we published our model spec. And one of the things is that we try very much not to give our models this freedom to decide to decide on their own whether the user is going to have good intentions or bad intentions. I mean, if the user comes out and tells you, I'm going to use it for bad intentions, then yes, you should refuse. And actually, our model spec says that. But generally, we have this transformation exception that says you could transform text even if it's bad, even if you would not, even if the text itself would have violated your policies to generate in the first place. And there are like two reasons. There are several reasons why it is, but let me say two reasons. One is that the user already has access to the text. And these kind of transformations are ones that you don't really need like a super duper AI tool to do. Like so, so in some sense there is not much harm in say doing spell checking or translation or I don't know, like making everything left align or whatever is that this kind of transformation. And the second thing is that there is often very good reasons to apply some transformation or classifications on problematic text, because the user might have, for example, for content moderation, you really do want the model to be able to say, to apply some transformation to be able to classify, and a model that just kind of refuses to touch any text that would be very useless for content moderation, or like sometimes you may be, you might be translating some historical book or doing OCR or something like that, and you don't want the model to suddenly like say, well, you've entered a bad book. So and generally we try to have most of our safety specification be intent free, because A, the model really can't peer into the intent, and B, that's what jailbreakers will do. They would say, no, I need it for my grandmother or whatever. So, yeah, but we try to actually leave less freedom to the model to try to decide on its own. Other questions? Yeah, so another thing that basically this method seems to help, and I think we need more, and I hope this also will be replicated by other people outside as well, but it does seem that it improves in terms of out-of-distribution performance. So say we trained on, we try to train a model with a data set that has no encoding in it. So no things like WOT13, base64, all of those kind of things, and nothing that's not in English. And it seemed to generalize basically within error bars to be the same generalization to prompts that do have non-English text or encoding as the model that was trained on the full data set. So it does seem to help in out-of-distribution generalization. So that's what I wanted to say about deliberative alignment, and then I'll move to inference-time compute and robustness. So now it's a good question to ask. It's a good time to ask questions about deliberative alignment. Yes?
I guess the inference time is not that big an axis here, in the sense that like none of these take a very long time for inference, right?
I mean, they could take, because I mean, like these policies could potentially, specifications could be long, but the main thing right now is that here it is crucial to have inference-time compute. It is crucial for deliberative alignment for the model to be able to think of specification. In fact, it is crucial for the model, like just for practical reasons, it is crucial for the model to be adaptive, in a sense that if you ask it, it would be kind of not a great model that we probably could not have deployed it if, say, if you ask it what is 5 times 5, it would go and enumerate, okay, let me recite let me check against the sexual policy, and let me check against the illegal activities policy. So in that sense, the inference time compute is crucial, so it only spends the time thinking about these policies when they're relevant. And, but it is true that in this work, we have not done this kind of thing where we scale this up or down, and this is going to be the second part. Okay, so, but it does actually, like, I mean, this first point that I said, I think it does actually point why I'm actually bullish about inference time compute, because it allows us to only spend effort on safety when we need to spend it. So I think if you had to pay a safety tax, where basically every single question that someone asks the model, it will have to spend a lot of effort on enumerating all the policies and thinking about them, then no one would be willing to pay it. And if we went to our customers and say, we're going to charge you 10 times as much because we are going to think about safety on every single question, then no one would be willing to pay it. But if you're like only spending it when you need to, then that enables it to be much more widely deployed. Yes?
Does this not open you up to attacks where somehow the user tricks the model into not checking a specification that it actually should have checked?
Yeah, I mean,
Sorry.
so that's a good question. Like, in fact, there is a question of like, say, how do you get the model to be more robust to these things where, you need to make sure that it's not being able to be tweaked. I mean, it does seem like, I think it does require more, I think require more study. But one of the things is that, it's not like the model is making the decision initially at just seeing the user's input, what policies would be relevant. For example, in the ROT 13 examples that we've seen, the model didn't know initially that the illegal activities policy would be relevant. It only kind of discovered it it only discovered it while it was thinking about it, and so I think that would basically make it much harder to tweak in the sense that it's not that you can do something that looks like a math problem, but it ends up being like about a bomb recipe. But maybe at some point while the model is thinking about it, it would realize that it's actually needing to provide the bombs recipe. Yes.
So what if a user asks some innocent request, and so the model would like not use it, let's check the policy subprompt or whatever, but will respond in like some harmful way? Like, would it be able to stop itself? So will this like check pass or not pass? Like, I'm asking about, I guess, the unintended harmful answer.
I mean, it's hard to know, but I mean, generally, I guess we are trying to train the model to apply. I mean, and I guess the nice thing about like thinking about policies is that you can set up a very low precision, high recall type of thing. So if your response could potentially be relevant, we are trying to train the model so that if your response could potentially be relevant to some aspect of your specifications, you should think about these specifications. And the nice thing is that thinking about the specification doesn't mean that you're going to necessarily alter your response, but it means that you at least consider it. And generally, yes, it's much better to spend a little bit more time thinking than to actually output something that is non-compliant. And we are like in training our compliance, we are thinking of it holistically. At the end, we want the model response to be compliant. It's not trying to assign blame whether the reason that it's non-compliant is because the user or because of the model. So there's definitely, compliance is not just, compliance with specification is not just about refuse or not refuse to the user. If you look at our model spec, it has much more than that. Any other questions? Okay. So let's continue. Okay, so if you want to talk about inference-time compute, then typically, as we've seen before, typically the graph that we see in any kind of ML, AI type of thing goes up and to the right. You spend more compute, you get better results. And That is actually adversarial robustness is one of the, maybe the one kind of counterexample to that, where this has not been the case that it has a problem that simply will go away with scale, that we don't have to think about, and we just pay more to the cloud provider, and it will just solve itself. So there have been several works and showing that basically we don't see this improvement by just simply spending more on compute on adversarial robustness. So generally, if we just spend more compute and we're not trying to solve adversarial robustness, then what we usually see is just kind of flat. Like it's not improving adversarial robustness. It's not hurting, but it's not improving it. Sometimes maybe there have been some I think it just mixed, like sometimes it's hurting, sometimes it helps a little, but generally it's just not doing much. And it is different when you're not just spending this compute in an agnostic way, just trying to improve performance, period, but when you're spending it for adversarial training, then you actually can improve performance, adversarial performance, but adversarial training has two drawbacks. One is that typically to have adversarial training, you need to kind of understand to some extent what the adversary can do. And in image models, it's a little bit easier because we have a pretty well-defined space of attacks. You want small perturbations on your images. But in language models, the space of potential things that the adversary could do is much larger, so it's harder to have coverage in adversarial training. And the second thing is that often when you do this adversarial training, you actually hurt clean performance. So you do adversarial training, the red line starts to go up, but then the blue line starts to go down. So these are the drawbacks with adversarial. And what we would have really loved is if we could simply have, like anything else we've seen in AI ML, that we just spend more compute without trying deliberately to solve this particular problem, and it just solves itself by sheer scale. And in some sense, what we see is that in inference-time compute, we get to some extent like that, something like that. So this is kind of a cartoon of how things look like. So basically, in that paper, we try to study this when we fix adversary resources, and the measure of adversary resources could change based on the type of attack we are considering. And then we see what happens as we increase inference-time compute. And generally, what we have seen is that for a fixed level of inference-time compute, if you increase adversary resources, then yes, probability of adversary success goes up. But for a fixed level of adversary resources, as you increase inference-time compute, then probability goes down, and usually to 0. So probability of adversary success. And here are some examples of what of this kind of thing. Obviously, the real experiments all never look as clean as the cartoon, but generally, I wanted this to be nicer, but anyway. Yes, so generally, like here are some examples. So here is the many shot attack, which is an anthropic paper where basically you just give in the prompt a bunch of examples of bad input and bad output, and see what happens. So as you give more examples, then the probability goes up, but as you spend more inference-time compute, the probability goes down. In this one, we had this language model program. This was like a black box adaptive attacker that gets queries to the victim model and tries to find some way to get it to output the wrong thing. And the definition of adversary success, we had like a bunch of data sets and a bunch of different ways what it means to adversary success. I think in this case, we had like some simple math problems, and the goal of the adversary was, so there was like a problem like 67 times 39, and the goal of the adversary was to put something here that would cause the model to output, instead of the answer plus 1. And here we have a white box attack where the the attacker has access to the weights of the model and optimizes to try to put some soft tokens here that would cause the model to output +1. It's pretty powerful attack, but again, like if it does seem that for a fixed level of resources, at some point here, like the level of resources that we measured was the train steps, then the increasing inference time compute helps. And we had some other things like a prompt injection attack and some adversarial vision data sets that we took from another paper and similar type of results. There was one counterexample that I wanted to mention. So there is one case where we actually didn't get this cartoon, where basically it seemed flat, like you spend more inference time compute and performance didn't improve. And that was on this strong reject data set, where we had the same black box attacker. And the interesting thing was that basically what the strong reject data set corresponds to basically some types of questions, and then there is some grader that says, okay, does the model have did the model give the answer to this question? And basically what the language model program attack found is ways to rephrase the question in a way that doesn't really violate our policies. And arguably, even the original question maybe didn't exactly, and this comes up to this question where the question itself might be asking for something that was not clearly disallowed under all possible situations, but was rather disallowed depending, if the user says they're going to do something very harmful with it, then you would refuse. But if the user says that they need it for some other reason, then you would comply. And so this kind of example just shows that, the inference time compute doesn't really, it helps you, but we still need to find this way of how do we phrase our policies and how do we make sure that they are unambiguous and precise. And this is something we're working on, but it's not like a solved problem. And so basically what we've seen is that, unlike agnostic training time compute, agnostic inference time compute, where we didn't do anything special with, like by increasing inference time compute, except just giving the model more of it, does seem to improve adversarial robustness. And my intuition is that the reason this works is that when you're doing training time compute, then basically you first train the model, then you basically give it to the attacker. So basically defender plays first and then the attacker plays second, because the attacker gets to choose the attack. And in some sense, with inference time compute, the defender gets another shot, because after the attacker provides the prompt, now the defender can decide how much to think about it. And the more complex or devious the prompt, then the more time the defender could spend thinking about it. So that's at least my intuition why I think this helps. Yes?
So I was wondering what happens if in terms of this metric of the resources that the adversary has, what if we allow the adversary to also maybe go forth, like it sees the context, it sees the response, and then maybe it comes up with a new attack?
Yeah, so I think right now, probably like right now the way our cartoons work is that this will succeed because, if we go back to, the basic shape, is that if you fix the inference time compute and increase the adversary resources, then you would then the adversary would succeed at the end. I think eventually what we want is to get to models that can spend an arbitrary amount of inference time compute, and then the hope would be that, say, if an adversary would do this loop, then they might end up doing something like a denial of service attack, but they don't actually break the model in the sense that they say, as they come up with a more complex prompt, then the model will just think longer. And then they come up with an even longer, more complex prompt, the model will think even longer, and eventually, like what will happen is just, the model will think for an infinite amount of time. This might be a denial of service attack, or maybe if the adversary is paying the bill, then it's just gonna pay for it. But it's not going to cause them. But we haven't done it yet. So right now we don't have like this ability to spend like an unbounded amount of time on inference-time compute. But I don't think it's fundamental that we can do. Yes.
So my question is kind of related to, but do you have intuition on what sort of dynamics could be at play when you have many like repeated rounds of interaction, but maybe the person on the other end is not so adversarial? It's just that their future inputs could depend on the past outputs of the model. Like for instance, let's say the first input was adversarial, but then you're just talking to a chatbot, right? You're just having a conversation. Like, do you think you could get some really interesting dynamics over time where, who knows, where the convergence happens?
I mean, I think it's generally dynamical and make it more complicated. But if we actually get to a point where the model could be relied on to be policy compliant, even in adversarial inputs, that's the beauty, right? The beauty of worst case analysis. Then you don't need to care about like how that input was arrived if you manage to get worst case the guarantees. And the hope is that eventually we could get something like that.
So in this plot, are you fixing some level of like success from the LLM side? Like I can trivially achieve adversarial robustness by just outputting like I am a dog to like every prompt that the user outputs, right? So like something has to.
So yeah, so in this prompt we are we are not doing anything like that. But on the other hand, we are not doing anything special like with the model. It's the same model. The model is not trained in any way or modified to be particularly adversarially robust or to always output I am a dog. It's the same model, and in fact we know from the previous prompts that as you increase inference-time compute, its performance becomes better.
Okay.
So,
so by inference-time compute, you're saying maybe increasing the number of tokens and
so basically it's the same way, the same plot that we had like in the very beginning in the O1 blog that say you increase the performance on Amy. So I agree, if just creating some model that has this plot could be cheating, but this is but the main thing is that this is kind of agnostic inference-time compute. This is not trying to be, is not aware of the attack. Any other questions? So this was the second part. So I just want to kind of sum up, and then maybe if there are, okay, let's go to, yes, okay, maybe, just say, I want to sum up that, there is, inference-time compute does not solve everything. We haven't solved jailbreak. There are still some issues, especially with complying with the spirit of specification, not just the letter. I think models can be actually pretty good at understanding intent. So I don't think it's necessarily the case that they could never follow the spirit rather than just the letter, but it's harder to measure, and it's going to be, there are going to be some questions. Like I think there are questions of like, how do you get inference-time compute to scale an arbitrary amount? Could you try to have like some theoretical models where you could show that adversary success converges to 0? I think that would be really interesting. And I wanted to end by saying this, I am AGI pilled in the sense that I think that, yes, AI, nothing is going to slow down, nothing is going to stop. So AI is going to be, to continue to advance and change society. And I think given what has happened in the previous years, and progress is just going, continuing and maybe accelerating, 2025 is going to be a very major year for AI. And I think whether, for all of us, whether at the industry or academia, I think would be very helpful to try to think of how do we ensure it goes well, how do we ensure it's beneficial for humans and it's safe for humans. So, and I hope all of us work on this question. Thank you.
Thanks, Boaz, for an excellent talk. We have tons of time for questions.
Yeah, thanks for a great talk. Maybe this is something you can't say, but what do you think is beyond inference-time compute? Like, it seems like a nice hack. Like when I first read about it a couple months ago, it seems like a hack that works really well, but doesn't seem like a principled approach. Like, feels like something is still missing. And your plots clearly show that, right? There's some examples where it's not working. Can you give some intuition on what you think is, the next step?
I mean, I don't know, like, I'm not sure, like, inference-time compute by itself, I would not call it a hack. Like, I mean, I would not call Turing machines a hack, in a sense. So I don't think inference-time compute by itself is a hack. So I think the main thing is like, how do you do it in maybe a very principled way that you could spend like an unbounded amount of time. So it will be truly like a Turing machine, like with all the, with all these things that you sometimes might not even be able to tell whether the LLM is going to spend an infinite amount of time or not. But that's what you pay for universality.
So, relatively speaking, I'm an old man, and I'm curious about like adversarial examples for vision models, like image classification. Classically, this is a problem that was studied by a lot of smart people for a lot of time, and it just seemed to be too hard, and we didn't come up with a good solution, and we moved on to other things. But I'm just wondering, do you feel like this approach has any hopes for resolving those problems? Either are there experiments done by you guys, or any thoughts about that?
So that's a good question. Like, I mean, I feel like there are several answers to it. So I personally have not worked on this, but there are two answers. First of all, I'm even older, and I think there is a sense in which, especially coming from the theory background, I'm saying, okay, yes, people haven't solved adversarial robustness for image models for a decade. But what is a decade? We have been working on P versus NP for like 60 years. So that doesn't mean that we cannot solve it. That's just, so I don't think we should necessarily give up. And it's possible that inference-time compute can help. But I would say that there is there is something that helps in the safety domains that compared to these other things. Because usually in this adversarial robustness for image, what you think is, okay, I have this model that gets 84% success on ImageNet, and I would like it to get also 84% success on adversarial perturbations. But and sometimes they might not even be possible to get like 100% success because there is some inherent ambiguity in the task itself. But if we do our specification right, then in principle, we should be getting 100% success in, or say, probability of success that goes to 100% as we spend more and more inference-time compute in policy compliance. And we should be getting that also with, with adversarial input. So one way I like to sometimes put it is the following. I don't care personally as a safety person, I don't care if my AI model takes an image of a pig and thinks it's a plane. But what I want to make sure that it doesn't take an image of a pig and thinks these are instructions to click on a phishing website. So I think the second problem might be easier than the first one, but I will not give up on the first one. It's just not the problem I'm personally working on. There was something in the back also.
So you seem to define the harm as a function of a task as opposed to as a function of an output. Could you talk a little bit about that decision? Why it's okay to I don't know, put out certain outputs as long as the task that they're the solution for is not a harmful one?
No, so I would not say that it's okay to. I think the definition is more, and again, if you look at the model spec, it's more, there are certain outputs that you might not be, it could be harmful in themselves. The main reason I was talking about this, we do have in our spec this transformation exception, which says that, say, certain output could be considered harmful for the model to generate on its own, but if the user already provided it, say it only asks the model to, say, spell check it or analyze it, then it would be allowed. And it would not, and that doesn't mean also that basically the model, say, if the user, for example, provided some, say if the user provided some recipe for how to create a bomb, and ask the model to count the words in that recipe, the model should do it. If it asks the model to go over this recipe to create a bomb and improve on it and make the bomb more effective, it should not do it. So it's not like it's a carte blanche. But basically, we are trying. With the model spec, we are trying to think of what would be the harm and look at it in the context of both the input and the output. And in some sense, if the user already has the input, then the harm would be minimal. And there are also very valid reasons, very beneficial reasons, particularly for content moderation, why you don't want to not touch anything like that's problematic.
Thanks for the great talk. So you have these strong negative results for watermarking in language models, right? So do you think are those negative results kind of untouched by the paradigm of inference-time compute, or can we hope to use inference-time compute to get better quality outputs with watermarking as well?
Actually, that's a good question. I didn't think about it. I mean, generally, the general result should still hold the same. The only way I could imagine it may be if we somehow, by inference-time compute, cause the model to start spending more and more and more time as the adversary mounts an anti-watermarking attack. But to some extent, I view these negative results of watermarking as ones that are actually become only stronger as the models become stronger. So inference-time compute, in some sense, might make them worse. And we have in the negative results for watermarking paper, we have some part that is actually purely theoretical, which we cannot implement right now, but we could potentially implement when the models become stronger. And the idea is the following. So what is watermarking? Just to kind of do a kind of a sidetrack. The general idea of watermarking is that you really have to rely on the entropy of the output. So to insert a watermark. But you could, as the models become more capable, a user could basically get the entropy down to 0 by asking the model to satisfy more and more additional side constraints. So the user could ask the model, okay, give me this story, give me a story about this and that and the other thing, but now I also want you to make sure that if you hash this story, then the first 10 bits of the hash are 0. So it could basically, the user could cause the model to reduce its entropy until there is no more room to put the watermark in. And inference-time compute won't help. Other questions? Yes?
I guess as a last question, unless anyone else has one. I'll ask as the last one.
Thank you. Yeah, I was just curious, given that OpenAI also allows for fine-tuning of large language models, and that there's also a lot of open source LLMs floating around. How robust do you see this, or how robust is this kind of stuff to fine-tuning?
Generally, probably not. It's not robust to fine-tuning, and I think when you're doing fine-tuning, you have to use some. You allow it for some customers, and you have to kind of maybe rely on some other measures of like control of like knowing who your customers are and trying to monitor. But yes, generally I don't. These things are not robust to fine-tuning as far as I know. And yeah, with open source, it's a big. It's not easy to. I don't know if it's a solved problem.
Okay. Thank you.
Anyone else? Cool. So I guess as the last question, this is a learning theory conference, and a lot of learning theorists who are probably various levels of anxious about the future for various reasons, but I'm just wondering if you have any thoughts, suggestions, advice, outlook for learning theorists in the era of these large AI models, potentially, AGI. What should learning theorists be doing right now, in your personal opinion?
Yes. Oh, good.
Keep calm and prove theorems, or are theorems going to be automatically proved for us so we're out of a job? Like, any thoughts?
Yeah, it's a good question, and I think everyone should. Yeah, different people should do, what. Generally, the advice that I've always given people is that they would be best doing the thing that excites them the most. So, I would note that somehow, for one reason or another, like OpenAI has like a huge number, like a relatively large number of theoretical computer scientists. So, yeah, it's. We could basically, basically start like a faculty club there. Like we have, like there's me, Madhvi, Valiant, James Lee, Bubek. So apparently, also a bunch of people are also have like some theoretical computer background. So it somehow seems to be useful, the theory mindset, even if you don't actually prove theorems. But if you are, I think there is still going to be a while where humans would have a lot of influence of what theorems to prove. I think it's going to be basically I imagine what the influence of AI is going to be fast, but also to some extent gradual. And we are not yet at the point where we could use LLMs. We are getting close to there. Maybe even we are starting to be at the point where, like in coding, where people use coding assistants a lot, we can use LLMs to prove a quick lemma. And I imagine that basically with time, these lemmas could be more and more meaty. And to some extent, that is also a great thing. I mean, at the end of the day, we want to understand the truth. We want to. I think a lot of us got into theory in general because we are really curious about various, big questions, big conjectures. And now, maybe together with LLMs, we would be able to explore them. So yeah, maybe I personally was obsessed for a long time with the unique games conjecture. Maybe now this can be a way to accelerate progress and to solve some of these problems. So I think there is going to be a long time or relatively long of like collaborations between humans and AIs. And it could be the case that supervising AIs to prove theorems requires slightly different skill set than necessarily proving theorems on your own, but we'll see.
On that optimistic note, let's thank Boaz again.